Hola, hola, hola. 1, 2, 3. Hola. Muy buenas tardes para todos. Gracias por continuar conectados al Congreso a través de...
Good afternoon. Thank you for keeping tuned into the Congress. We invite you to use the social media using COLOMBIAMAR 2021, mentioning COLOMBIAMAR, COLTECMAR, continuing with the agenda. We continue with the agenda, and we are now going to enable 2 channels to have access to the presentations that will be concurrent according to the topics to be addressed. So, the ship works 4.0 and competitiveness of the industry. You will be able to access www.colombiamar.co. The first presentation for today is called Speed, Control Vehicle, and Heading for an Unmanned Vehicle. Analysis of various algorithms applied to the control of navigation in USB, and is in charge of Messrs. Carlos Gutierrez and Lieutenant Lalo Garces. Gutierrez is an electronic engineer specialist in industrial electronics with expertise in oceanographic instrumentation, unmanned vehicles. He has published several pieces. He's currently a professor and researcher in the Almirante Padilla School. On the other hand, Lieutenant Garces is an electronic engineer. He's a specialist in industrial equipment and process automation. He's an expert in radio frequency communications, radars, and combat management systems for military uses. Since 2015, he's been working as a researcher for the tactical networks in the Navy of Colombia. I leave you with Mr. Carlos Gutierrez.
Muy buenas. Estamos aquí hoy entonces para presentar el sistema de control de velocidad y rumbo. ¿Ya está prendido? Estamos aquí para presentar el sistema de control de velocidad y rumbo del vehículo de superficie no tripulado que tenemos en la escuela naval. Para hablar de esto, primero...
Talk about this. First, we will talk to you about
cómo fue construida y cómo
how it's built and how the onboard system works. On the other hand, we will present to you the control scheme that we have presented. Also, we'll talk about the sea trials and the results we have obtained. In the first place, as you can see, this is a platform, a 2.5 meter in length, 1 meter of beam. It's got a jet propulsion system and with a device to a heading device, providing this vessel with maneuverability. It has an inertial sensor, GPS, which we've been using mainly to be able to implement this control system. This block diagram is basically the system that we have implemented on board. It's got a compact river. It is a technology of National Instruments, and this technology has been certified by classifying houses to work in marine environments. Therefore, even though it is quite costly, it is robust, and that is what we are looking for. So this platform receives from above a data link, and this data link is used to communicate directly with the control platform. Likewise, it you see connected via serial port, the GPS, the inertial sensor, and it have auxiliary sensors such as the speed sensor via ultrasound, an eco probe to measure depth, and in the future we will implement via Ethernet LIDAR. Also, it has thermal imaging cameras. This is likewise. Tenemos problemas. There are both the driver of the engine as well as the reverse pallet as well as the servo motor. We have set up a control system on top of that system. In the first instance, notice in the image above where we have a heading loop control loop, and a control loop that are a variable speed control loop independent from each other. And this controls the variations. This controls so that heading variations do not exceed 30 degrees. That is, if I'm heading on 010 and I want to veer to 020, that is a turn of less than 30 degrees, so the system can perform independently. In the future, our intent is to implement a coupled control loop as the image that you see below, where the heading of the rudder will also have a direct effect on the speed control. And this because the ship, as it veers, as it turns, the ship loses a speed, and if we can have control on both, then we must also guarantee that the speed is maintained whether or not the ship is turning, but that's a future implementation. And it is worthwhile mentioning it. Now, this 30-degree threshold is relative because it depends on the size of the ship. Notice that this is a ship which measures 2.5 meters in length. If we use a larger vessel, maybe the threshold will become smaller. But the heading and the speed loop, that's important. They can be worked on independently. We would need to evaluate the threshold depending on the size of the ship, but it is something that we can do normally with the maneuverability test. And these are tests that we were able to implement with this boat. And this test, which is the evolutionary circle test, and it allowed us to understand the dynamic of the boat. And with it, we were able to come up with the mathematical models to describe the behavior of the vessel. Now, we did this test because it was a regulated test. The National Maritime Commission has proposed this, or the authority has proposed this test as one of the maneuverability tests that must be performed on any ship. And it is precisely for this reason that we prefer to use a normal, a regulated test. Nevertheless, that test, we implemented it in 3 phases. An initial phase where the propulsor, the driver was in 0, as well as the rudder. A second phase where we throttled up the ship until the boat would stabilize the speed. That's when we turned. You don't see the image, how the circular wake is generated as the boat navigates, and that circular wake is precisely that which allowed us to understand the dynamic of the ship. Now look at this graph, for instance, and this shows us that the speed, and notice that for a power of 45% in the throttle, it is an average speed of 3 knots. And notice that it took less than 8 seconds to stabilize its speed. Again, remember that we are talking about a very small ship, 2.5 meters in length. Obviously, these times change as the size of the ship changes, which is why Every time you come up with a new ship, you have to do these tests again. Also, notice the purple curve, at the instant when the moment in which the rudder changes is moved, and notice how the heading center start to vary in a linear manner. You see a circle is seen as it didn't matter how many times it went round, it was turning in a stable manner. All these tests allowed us to understand which were the most for speed as well as the heading. Notice that the heading model, the speed model is dead, and the heading, it is a second order model. It is very known and widely used in maritime ship. What you see there precisely shows you how the first order adjusts to the experimental tests. That is, we came up with a correlation between that experiment and the signal, and the mathematical model, and the correlation is higher than 95%, which allowed us to conclude that in fact both the model adjusts to the dynamic of the boat. This way, for the speed control, we're able to implement a PID speed control. And notice this is a simulation. When demanding a 5-knot speed, the PID controller took 6.13 seconds to gain that speed, showing that the constant of the controller, in fact, are able to control the mathematical model. And this is what remains for us to supplement. Likewise, we implemented integral proportional controller for the speed model. And here we can see how that speed model, less than 6 seconds, was already stabilizing the heading of the system. Now, these are preliminary results but the investigation is ongoing. It is also important to highlight that the sea trials are soon to come. It is important to highlight also that the mathematical models were done as shown with experimental results. Now, an important question, actually a relevant question, why is this important? Why is it important to implement navigation control, a speed and a heading control? I would like to mention two things. One is that when the moment we developed all these technologies for ourselves, Colombian development made by Colombian, we are improving our technological independence, which is a relevant goal for the Colombian Navy. Also, the work with unmanned vehicles, the development of unmanned ships, is part of the 2042 plan, which is the Naval Development Plan. And then continuing with this work, these two control groups are essential for subsequent navigation profiles or navigation planners. And that is what comes next in our research.
Buenas tardes a todos.
Good afternoon, everyone. Next, we will present an analysis that we performed on various algorithms applied to the control of navigation for its application in unmanned vehicles, surface unmanned vehicles. The idea behind this work was to supplement the work previously presented, where the navigation control system is proposed from the lower level. That is, from the effect that the controller has on the actioners of the vehicle in order to move it, right? To to then analyze an algorithm that you find in a higher level, which is what give the order of that controller to then maneuver. The next presentation we will divide in 4 parts. We will do an introduction where we will explore different basic concepts on the concept of navigation in unmanned surface vehicles. Then we will do a debriefing of the various navigation algorithms, and we'll try and get to know it and learn about its philosophy, to then move on to an analysis. We're taking as the basis some metrics that we've selected, right? And we'll do a qualitative analysis to try and provide you with some selection guidelines, right? In a scenario of an unmanned vehicle with the presence of known obstacles, to then move on to conclusions and recommendations for work. So to start, the most important is to define the concept of autonomous navigation, which is nothing more than the technique that allows an unmanned vehicle to move from an initial point to an end point in an environment with the presence of obstacles, whether known or unknown. In that sense, the goal of a navigation algorithm is to take that vehicle from point A to point B. That is, algorithms are the applications of that autonomous navigation technique that we referred to previously, always considering that within that route or that trajectory that the vehicle is to follow, you may encounter different obstacles which might obstruct that path. So we studied 3 different branches of navigation algorithm. We could refer to them as branches or families, depending on the function. The first family of navigation algorithms that we studied were the algorithms based on reactive navigation. What is the principle of functioning? Well, as its name tells it, these are algorithms that do not think, colloquially speaking, but actually receive information from the environment through its sensors, and the decisions it makes are made in reaction to. That is, they receive information through their sensors, and when they find an obstacle, its reaction is to perform a movement to evade that obstacle. Now, in that set of algorithms, we identified 3 subfamilies, each of which, each according to a very specific principle of operation. The most basic algorithm is the bug, of which an entire family stems, which principle is to start the trajectory from point A to point B, and as an obstacle appears, follow up on that obstacle to be able to evade it. And that concept is known as border follow-up, which means the vehicle is just treading along, and once it finds an obstacle, it sides it goes through its sides, and after it completes its run, it identifies the best point in which you should veer away from your heading to then come back after having avoided that obstacle. Now, algorithm that work according to that methodology, we selected 2, which are those that exhibit the best performance, bug 2 and this bug. Bug 2 works by taking as basis an imaginary line between point A and point B, and the vehicle simply follows that line. When it finds an obstacle, the vehicle evades it by performing the sideline and the bordering of the obstacle, and once it gets to the line again, the vehicle abandons that obstacle and continues on its trajectory. In the case of this bug, What it does is to internally calculate the distance between the point it is at then and the end point. Once it finds an obstacle, again, it borders it, but to get out of the obstacle, the condition that triggers it is to find a point in which the distance right then and there at that point with respect to the end point is less than the point where it found the obstacle. So it starts going around the obstacle, and when it gets to that point that is closest to the end point, it takes to that heading again. Then we have other methods, other algorithms stemmed from the bug family, and we selected Rev1 and Rev2, which are basically evolutions of bug2 and disbug. Rev1 is an evolution of bug2, and Rev2 is an evolution of just bug. Now, what is that evolution all about? See, the original bug algorithms, when avoiding an obstacle, they always turn to the right, to port side, starboard. So they find the obstacle and they turn starboard and they go around it. When they find the next obstacle, they do the same thing. And if they find another, yet again, they'll do the same thing. So this algorithm has the capacity to decide the direction of the turn. I mean, they're not always programmed to turn right, but depending on how many obstacles might have come across its path, if the vehicle should be in a position through which it would already have navigated through, it can turn to the other side, and that allows it to optimize the possible navigation route or prevent. And in some cases, the algorithm is trapped in a circumnavigation condition that we'll look at later on. Another family that we analyzed is a very specific algorithm that is known as follow the gap. Now, this works this way. The intent is to look for the gaps between two obstacles. It calculates the angle of that gap that exists between the two obstacles, and it just simply navigates with the calculation of that angle to go through the center of the two obstacles. And so following a trajectory through the holes found along the obstacle route, it tries to move. Then we had the deliberative navigation algorithm. These are more complex algorithms. They are more intelligent algorithms, which no longer react in the face of an obstacle, but they now actually generate from the beginning a route that will allow them to get from point A to point B by avoiding all the obstacles that should appear. And for that, they use a technique referred to an SLM, localization and automatic mapping. What does that mean? That the vehicle just is moving along, and with its sensors, it is absorbing information from its surrounding, and little by little, it constructs a map of that environment that it is displacing or going through. And with positioning the sensors, it places itself in that route. So vehicles working with this algorithms know where they are and know where they're going. So in this family, we selected 4 algorithms. This is tangent bug, that while still bug a family algorithm, it is somewhat different because this algorithm requires knowledge, some knowledge of the environment. Why? Because it identifies all the obstacles in the environment. That is, it is familiar with the environment, and then it moves through the vortices of each obstacle. That is an obstacle here, there, over there, and it creates a trajectory, a vortex to vortex trajectory to reach the end point. Then we see the algorithm on which the other two are based, which is the Dijkstra algorithm, and it is an algorithm designed to enable the vehicle to determine what the shortest route is, what the optimum route is to get from point A to point B. So what does it do? It identifies the entire surrounding. It divides the surrounding in a grill, and each square of that grill behaves as a station. a grid, not a group. And then the vehicle calculates the shortest route to go from one box to the other, from one station to the other. So it generates or it calculates distances in a straight line or diagonally to use the shortest route. And that way, it calculates many routes. And then, with all those routes it calculated, it selects the one that yields the least distance. And then we see the A star algorithm, which is an evolution of the Dijkstra. And as opposed to the Dijkstra, the A star, when an obstacle appears, the A star is an algorithm that, okay, it had all its planning already, but the moment an obstacle appeared, it did not need to go back and recreate the scenario and then execute the algorithm to be able to continue, but actually is capable of reacting, of avoiding that obstacle and take one of the routes that were previously calculated. And then we have the delta star, which is an optimization of that A star, right? And then last, we have algorithms that are the simplest of them all. The functioning philosophy is based on the follow-up of navigation bands. So those are algorithms that are used when we need our vehicle to move through a trajectory. That is, we give them a route, a path, a heading, and the vehicle needs to follow it regardless of the presence of obstacles. And there are three different algorithms: the curve 1, the curve 2, and curve 3. Differences are that, well, curve 1 is the simplest one because they just get a path, the simplest path, point A and point B, with either none or some obstacles. In curve 2, you will see more than one intervention. In curve 3, there are multiple intersections. It is according to the navigation route. The point might have to go through the same point several times. So this is useful for vehicles that have a predefined mission. We might force it to go through one point several times to accomplish the mission. So subsequent to that, we will now analyze the navigation concept, and we're very much tied to the algorithms that we've mentioned. What is planning? There are two types: global planning and local planning. The global planning is the generation of the route, which allows you to define an obstacle-free path from the beginning to the end. And since the beginning, it knows where it is, what the environment is, and it plans the route. The local planning is the capacity that a vehicle has to modify that route that had been previously defined according to the apparition of obstacles that were not counted on. So you have a path, you had to find a path, then you had obstacles, and then an unplanned for obstacle appeared, and the vehicle has to react and then do an on-site planning, which we refer to as local planning, on-the-spot planning. So, having described what we are going to analyze, let's then move on to the analysis to try and find what or which were the algorithms that exhibit the best performance under certain particular conditions. So we did a qualitative analysis on the algorithm, but basing ourselves on two concepts: general performance and required resources. General performance, we analyzed detection of the concept of circumnavigation, that is to come back through the same point, the length of the route, the distance, and the capacity to evade obstacles. And the required resources, well, memory requirements, processing requirements, the number of sensors we require. So we analyzed each algorithm and we analyzed which performs the best. For instance, the deliberative navigation algorithms are excellent to detect circumnavigation. Those are the ones that exhibit the best behavior to calculate the length of the route. They are very good to evade obstacles, although in this specific point, the reactive navigation algorithm are best because they're done for that. And then we analyzed the required resources, that is memory, processing, and the number of sensors required, where the most complex algorithms, such as the deliberative navigation algorithm, require more resources, right? More memory, more sensors, but as opposed to, they offer a better performance. So we did an analysis applying weight to each metric. And then after that analysis, we started as a qualitative analysis and ended up being a quantitative analysis. We find that the Delta Star algorithm exhibits the best performance based on the weighted result. It is excellent to detect circumnavigation. It is excellent to calculate the shortest route. It is very good to evade obstacles. It is castigated in terms of resources. That's its handicap, but its great performance behavior compensates a lot of the resources it requires. So the main thing of the D-star algorithm and why it works as good as it does is because it uses the SLAM technique and because it is an algorithm thought to carry out global planning tasks. So it is an algorithm that can, during the initial run of the vehicle, detect the environment. It is ideal to perform that local planning, but when it has to do global planning, that is when an obstacle that was not counted on appears, it has the capacity to react. Other good performing algorithm that we found is A-star. It is a slightly less efficient than the D-star. Rep 1 and Rep 2, while reactive in nature, are algorithms that, for the cases where there is no large quantities of resources of processing or memory, there can be a good alternative because they guarantee the vehicle in terms of it going from point A to point B, not necessarily via the shortest route, but at least they guarantee fulfillment of the objective. Tandem also obtained a good result. The other algorithm, from the analysis that we did, its performance was less than 3 and were therefore not considered as options with good performance. Basically, from this analysis, we learned that the deliberative navigation algorithms exhibit a better performance than the reactive navigation algorithm because they have more information from the surrounding areas. I mean, they know where they are going, what is around them, and therefore are able to make better decisions. And what is good about the reactive algorithm is that when they find an obstacle, they are the best at avoiding them because they are designed for that, but they do not guarantee that they'll take the vehicle from point A to point B via the shortest and most efficient route. It guarantees the vehicle will not crash. That's it. And finally, after all this exercise, we found some conclusions, which I've already mentioned. For instance, like the Delta Star is among the algorithms with the best performance of those that we analyzed. It was the one that behaved the best. And should we desire to use a surface unmanned vehicle in a setting with very few obstacles, that would be the ideal algorithm for that. We've already talked about Rev 1 and Rev 2, which we can use in situations where we might not have enough resources in terms of memory processing or sensors, but which will yield us an acceptable performance. And finally, in scenarios with a high density of obstacles and where those obstacles might come to view unexpectedly, the recommendation is to use 2 algorithms, one to use global planning and the other to use local planning, one for deliberative navigation and another for reactive navigation. And that was the result at which we arrived with our work. Thank you all for the attention. And we now extend the floor to Carlos. Thank you, Lalo. Now, there's a question in the chat. It says, and I'll summarize it into one. Why do they pegging or heading and not PWM? And the implementation of the control system is for calm waters or outer sea waters. Why do you peg in system for heading and not a PWM one? That man's what happens is that the technique that we used to sync the heading center is a technique known as the synthesis of Dalit. The Dalit synthesis, what it does is that once you know the transfer function of the process, in this case, is to determine how you want the system to behave. And having determined that, then you can infer what the transfer function of the controller is. Having we went through this process with the Nomoto model, and the result was that the controller to use was a CIP controller, and that is why we used it. I'm sorry. Pain controller. Nevertheless, it is important to highlight that the Nomoto model proposes or presents a process that is not self-regulating. So, in light of the literature, when you have such a process, not self-regulating process, the best thing is to implement regulating control. Thank you, Carlos, for the response, and Lalo for this presentation. Very kind. Thank you for your participation. Thank you. The next presentation is in charge of Rear Admiral Carreño, who is a professional in naval engineering with a master's degree in defense and national defense. And he is a graduate of Politécnica de Madrid. His research interests are focused on the technological development and innovation in the naval industry, ship dynamic maneuverability in shallow waters, and experimental hydrodynamics. During his career in the Navy, he has held several positions, among Chief of Engineering of the Technical Department of the Naval Base Arce Bolívar, Director and Chief of the New Constructions Group of the Science Construction Technology, Vice President, and then President of COTECMAP, General Inspector of the Colombian Navy. He is currently CEO of Genova, Colombia. Today, he talks to us about challenges in naval and construction in the 21st century. With you, we are Admiral Carreño. Thank you, everyone. Good afternoon. A special thanks to the organizers of this naval engineering and design and engineering, to the director, the Navy, and to our Colombian and Latin American colleagues who for so long have been working together for the advancement of the Colombian industry and that of the region as well. My presentation I've titled Challenges of Naval Design in the Latin American context of the 21st century. And it deals, it's but a summary, a brief summary of a context of the sector in that which regards industrial policies, defense policies, and a small analysis on how development is affected, particularly the design and the engineering of naval platforms. I'll talk about the most relevant projects that we find in Latin America today and some drivers for those projects and impacts, of course, on the industrial, social, and technological spheres of countries that involved in those. And finally, a presentation on who we are, Genova, our capacity, our experience, and our bet for Latin America, but particularly for Colombia. Right, now, let me give you a bit of context of the sector. The industry, the ship building industry is a complex industry. And that makes it an interesting industry, a protected industry in many countries. And the complexities of this sector deal firstly with the ship, because the ship is the biggest and most complex capital asset that a man builds. It is a floating city that implies every component that provides it with autonomy, capability, and autonomy that goes hand in hand with a technological development, right? That's why ships are not sold in series as cars are. Each project is a complex, specific project based on missions, operational needs, operational environment, the needs of logistics support, and also complexity in terms of these systems. On the other hand, this is a labor-intensive industry, but skilled labor at the level of engineering, design, also technical management, logistics management, and overall management skills, which precisely because it is a labor-intensive industry and associated, linked to that complexity of the ship, it acquires a specific distinction. Also, because of its interconnections with other productive sectors. Also, the classification houses, the universities are fundamental in generating this skilled labor. The ship owners, the design officers, which is the focus, my focus on this presentation in terms of the needs of design and the degree of technical art that we need to go from the sketch to the delivery of a ship, including the contract, and then the 30 to 40 years of life of the ship until its final decommissioning. Finally, the role of the state in various roles in Latin America, particularly the state assumes different roles in the shipbuilding sector. A role is a regulatory role, of course, because governments issue industrial regulations, industrial tax, defense policy, but also the state plays an owner, the role of a ship owner, because the state owns companies that operate, whether civil or military fleets for different purposes. But then we have the shipbuilding state, and that is particularity in Latin America. The shipbuilding state, that is the state that promotes the industrial sector through the operation of shipworks, and of course shipworks as such. And it is an industry of synthesis, as most war navies describe it, because in most cases we agree with this vision that we have in the 2042 plan as it is published in the webpage. It is an industry of synthesis because it is an attracting industry. That industry pulls other industrial sectors that link up with it, as you know, the electrical sector, manufacturing, trade, with very interesting indicators I'll show presently. Metal mechanics, materials, polymers, electronics, and the 4.0 industries, which have been the subject of today's Congress during this morning's session. Now, talking as to the complexity of the sector within the framework of public policy, and by this I don't mean exclusively to Colombia, but overall, the public policy industry-wise includes components that have an important effect on these projects that are embarked on by shipwork, both public and private. Policy is always puts into scale the promotion of the industrial activity and or the promotion of international trade, and necessarily the two don't row toward the same direction. A policy that has just been issued by the Colombian state not necessarily incentivize the construction of ships in the country, because if you incentivize the bringing of other ships, that incentive might go against a public policy to construct locally. On the other hand, the tax policies, the ships are capital assets, and most countries regard it as an asset. And if they generate wealth, they're not taxed with, say, VAT, precisely because capital assets are there to promote development and the generation of wealth. And so they have those considerations. But in Colombia, it hasn't been, that's not been the case. And there has been a strong opposition or a fight from the sector, for fair treatment and equal conditions, not only in tax matters, but tariffs matters. Also public policies that favor the financing of I plus D plus I. So by that we talk design, construction of ships, technologies associated to the shipbuilding sector. Those are absolutely necessary. We saw digital developments, the new shipwork, the new energy sources. We're talking about carbon footprint or the decarbonization. We see commitments by 2050 as acquired by countries, but those commitments are not accompanied by technological development nor the mastery of certain technologies. So there is still a gap in terms of resources invested in I plus D plus I in certain areas of knowledge, particularly in the shipwork sector. Now, sectorially speaking, there is a role for greater private participation, but which always requires support from the state. By that I mean the private clusters that unite around an industrial sector. In Colombia, in the last 2 years, we've seen the rise of the maritime cluster in the Chamber of Commerce of Cartagena as a leader of this project. Cartagena being the city in Colombia where the most capacity of shipbuilding and shipworks exists, with important foreign trade policies, providing incentives so that other goods and services companies come on board. Also, to improve their standards vis-a-vis the possibility of exporting goods and or services. We can also talk about innovation, such as a bet of a sector to not follow behind in terms of key technologies and knowledge that must be applied to ship projects. And lastly, industrially, the infrastructure has an effect on the possibility of undertaking projects. There's a strong limitation in the case of Colombia. in terms of the lifting capacity, and we see like in the last few years, the main shipworks have created growth projects to improve their lifting capacity. There's been a bet made on the training of human capitals and the appropriation of technology, and that perhaps has been that bet by Colombia in the last 20 or 22 years has placed Colombia on the map, in the regional map of the shipbuilding industry through COLOMBIAMAR. You see it reflected in projects with national content, with our own development, also with co-development, evolving from the policy that existed prior to 2000, where in most projects the acquisition strategy was precisely to buy. Anything built abroad today, most projects are approached from the co-development point of view, or a wholly local development point of view. In Latin America, I said that the defense sector has been one of the main drivers of the shipbuilding industry. In almost all the countries where there's been an important development, the technological strategy and the innovation of the defense sector is open naturally to the development of skills to incorporate platforms that will make it possible to achieve the objectives of the need of the region's navies. That's like part of the strategy, but that strategy has several parts, like in terms of security, purchase, develop, or co-develop, right? And in the case of those strategies, those that have opted for investing in self-sufficiency and investing in human capital and technology, that either via technology transfer or to develop some, well, the end would be to attain the technical mastery. And by that, we mean the transfer, the knowledge of a technology, but linked to its ultimate use, to its application in a given project. And that technological sufficiency also makes it possible for the defense sector to promote those maritime interests as they reflect in a technological tool that allows us to not only promote the defense industrial base of its own country, in this case Colombia, through not only the defense sector companies, but also those reflected in the shipbuilding sector, the industry that cooperate with the main ship works in Colombia, which through different initiatives they are grouped in clusters or industrial sectors, or those which cooperate with the Pan American Institute of Naval Engineering, but promotion anyway. And that ultimately turns into a strategic tool for the country, because the navies would then not only through those skills developed in the country would satisfy their own needs, but it would be able to then take a proposition of cooperation defense-wise to other countries. In the case of Colombia cooperating with Honduras, with Guatemala. And I mean exporting technology, but also doing technology transfer, training people, but based on a project that was developed and operated in a country such as is the case of an amphibious boat, or in the case of Brazil, where they incorporated the armored fluvial vehicles, river boats, of which currently there are 4 operating in the Amazon River. Now, that's the regional picture. And in this map of Latin America, I have chosen some important projects where we see how each country, particularly each navy, has adopted different strategies to acquire its capabilities, develop local content, and just forge ahead with all the benefits that this sector generates. From north to south, let's start with Mexico. The Pola, the ocean-going, the patrol boat, the Mexican government selected a technological a partner which was Dame from Holland. And they prioritized one first ship that is already constructed and operating. It was a technology transfer and construction, a modular construction. The most complex blocks were imported into Mexico. They were conceived in Dame shipworks, and some blocks built locally in Mexican shipworks, generating local jobs and generating knowledge in the different areas associated to the management of programs, the technical area, the production area. And that was the strategy that Mexico adopted. It is a ship that, although known as a patrol boat, it is pretty well equipped and armed. Moving along with the Pacific, or through the Pacific, we have Peru, but we have Ecuador. Last year, perhaps at the beginning of last year, perhaps late in 2019, early 2020, the Ecuadorian Army unveiled the multi-purpose diamond ship to be constructed completely in a local shipworks. The Astinave shipwork, which is a publicly owned shipworks, where the Navy has an important stake. And in this case, well, it transferred the design, package of materials, technical assistance for the ship to be built locally in Peru. In the case of Peru, CIMA, the Peruvian Navy, took on a production program cooperating with the Korean shipbuilding shipworks, STM, right? And there are CPB, several are operating now. So local construction also in Peru in a cooperation strategy, but with a completely Korean design, just like with the previous projects in Chile. The strategy has changed slightly as compared to the previous projects, because Chile no longer picks a ship works as a partner, but it goes out and contracts with an engineering firm to build that ship. The Antarctica 1, it's an icebreaker. It's an advanced ship in every sense. It's important, and it is being built in the Talcahuano plant in Chile with the management, the technical, operational, and logistics management of ASMAR and the Chilean Navy. Recently, also, the Chilean Navy has announced the selection of a design office or a design supplied by the same office that supplied this icebreaker project, Antarctica 1, and that is going to be the next project that Chile will embark on with this same strategy, the ASMAR strategy for the Chilean Navy. And turning around the Strait of Magellan, we have one of the most relevant projects being advanced in the region, which is the Tamandaré class frigates. And we have the Siemens Club system is developing the project along with, together for the Brazilian Navy with private shipworks, because as opposed to other Latin American countries, in Brazil, shipworks are mostly operated by private capital. Brazil is a country that protects its own industry. The construction must be 100% local, with a very important local component, by the way. And lastly, Colombia. I brought two projects that you see on the slide. The one to the right is the next generation of OPV ship, referred to as OPV 93 Charlie, and that is the length of the project. It exceeds the previous projects by 13, because the previous projects were 80. So it is now going to be a local, 100% local development. A COLOMBIAMAR development for the Colombian Navy. It's been under development for 4 or 5 years. I think it's mature, and I think it's practically ready to start contracting. And this would be the first project in the region with 100% local basic engineering, and that is an important reference. And to the left, we have the strategic surface platform, as we all know, is the Almirante Padilla class frigate, which had near the end of their cycle, and they're to be decommissioned. But this project has been evolving for 12 years. The planning and the requirements are almost completed, and the Navy, the Colombian Navy, is ready. Of course, the moment the funding is available and the high-level decision is made, we will go out to the international market to look for a technological partner to approach the project according to the conditions being set out by the Navy. And which are those? I found on the Navy's webpage, published maybe at the beginning of the year, what they referred to as PRESCIENT. PRESCIENT is the construction and the naval construction and optimization plan. Below, you have the quote, the 2042 naval development plan. As I told you before, it's been published on the website of the Navy, and it includes a very clear definition of the capabilities to be incorporated. It has a defined time horizon, of course, subject to the availability of resources, as with all these projects, but at least there's a north. There's a definition that allows the industry to either public or private, as is the case of the Genova, which is an international design office, well, to plan and make decisions when investing resources and betting for a country or a region. Now, this plan, and I brought this slide, again, quoting this naval development plan, shows us what the renewal of capabilities is that the Navy is projecting or forecasting. From below, two sea patrol vehicles, which will surely be acquired through an acquisition purchase or a strategy, a multi-purpose vehicle, which surely the strategy will be 100% local, given the history and type of projects embarked on by Colombia, the OPB 93 Charlie, which is the patrol with local develop the submarines, the renewal of its submarine fleet, surely a purchase to not bring technology to Colombia that may be truly expensive and which Colombia might not actually want to approach a business line as such. And then the frigate project, which is the project where the acquisition strategy defines as a cooperation to be built in a national shipworks that is in Mar and with a 40% local content. And this is the novelty because it is highly demanding content for a program of this magnitude. Local content at 40% in a program of such magnitude where the main systems are imported, as are the combat systems, which are costlier. And in the platform, every propulsion system, the generation system, all the auxiliary systems are truly a risky bet. It's good to have as reference, but strategies will need to be defined or designed at the public level to meet, attain this. We are told in this, we're set in this development plan that there is 9,800 direct jobs and more than 30,000 indirect jobs. This program, as is the case with any defense program, has a timeline. And that goes through the refinement, the fine-tuning of the concept, which take at least 8 years. That is what the PES took in the Colombian Navy. And the development of the technology which ends up with a preliminary design of a contract, 4 years. That's 12 years with analysis, planning, engineering, construction in different environments such as simulation, different boards, technological evaluation, systems evaluation, technological benchmarking, evaluation models to then reach the point of signing a contract 12 years then later. And then 8 years after that, we would have the first ship Well, the first ship, as for sea trials, we're talking about complex projects that take at least 20 years to develop a warship. And in this process, the most demanded resource is known as knowledge, engineering, in its various disciplines, and ultimately the sustainability. That is the 30 or the 40 years of operation of a ship. That's the average in our region. And I call your attention to the integrated logistics support. And that is because that is perhaps one of the most important bets. This morning, we talked about the digital twin and how the 4.0 industry is pointing towards the management of the integral logistic support and the life cycle of the ship to optimize it, to increase reliability, to decrease costs, etc. In terms of engineering resources, we are talking that we're saying that for a frigate, it would take over 1 million man hours. All that process that I mentioned, a light frigate. And we would need about 100 people in an office working for about 10 years from the basic engineering phase going into the detailed engineering and then in parallel the integrated logistics support. In summary, the challenges for that, which I've just described to you, go through the local content, which is very hard to meet in every area. Companies that supply engineering, companies that supply metal mechanic services, electronics, consultancy, for all the areas that a project of such magnitude would demand resources from. But then we have intermediaries, parts, systems, components. And since a country cannot develop the whole thing, we can at least motivate, encourage the national and international sector to invest in Colombia and bring their technologies and manage it locally. But from the structuring of these large projects, it would then allow them to land in the region, right? And then going for the entire industry in the region. So any country that intends to have or commit to this project, well, it means a big challenge. And the country will have to commit. And that, the role of academia and the technological development centers, it's essential. You need the participation of universities. You need the participation of technological development centers if we actually want to see these projects come to fruition. Now, qualified human talent, the new technologies that in 20 years of evolution of the project, that is the project that is started is not the same project that is delivered, much less the first ship of the series will be equal to the second or third or fourth. Cooperation and technology transfer is essential because when we're cooperating between an owner or a shipbuilder or a combat system vendor with a navy or with a local shipbuilder, you need to have capability to absorb. There needs to be in place a local organization that will adopt all of that. Now, flexibility and modularity, because of the technology and the changes in mission, the incorporation of new missions through time, new challenges, and lastly, sustainability through the life cycle dependency, logistics dependency, the dependency on vendors, the capability of upgrading the ship, the capacity that the country must have, the shipbuilders, the navy, to manage the life cycle while minimizing costs and increasing reliability of the platform are huge. And then to end, this is the proposal that we have made as an international design office, a world-class design office, and particularly in Colombia. Genova is an engineering office. It is the most important naval engineering office of Spain, with over 450 employees, engineers and technicians, projects in over 25 countries, and we have installed 750,000 hours. We work 750,000 hours of work of work per year. We work on that digital transformation. You look at the office below, and that's the office we have in Cartagena, Colombia. We are operating in 5 countries: in Spain, where our head office is located, in Australia, and in Latin America. We've been in Brazil for 10 years, in Rio de Janeiro. In Bolivia, there is an office where we have the renewable energy industry and infrastructure. And in Colombia, the bet was made in December of 2019 to become the most important naval engineering office in Latin America. We currently have over 40 employees, Colombian employees, most of them, all of them, most working in Cartagena, generating jobs and generating national participation in the large projects, not only national but international. So they are generating services exports in articulation with our entire network, generating trust out of the experience, which comes from the experience in projects, consultancy, basic engineering, detailed engineering, technical lead, and integrated support. That is what we move. And as a reference, I want to show you, this is the last slide, I promise, where for over 25 years, particularly in the last 5, Genova has participated in projects such as the air carrier in Turkey. Just that took over 700,000 hours of functional and detail engineering. The strategic service platform, the Colombian Navy received the consultancy to define requirements in 2018. In 2019, in the last few years, ever since 2019, we've been working on Plaza Vante 2200 for the Saudi Arabia Navy. Again, we were heavily involved in functional and detail engineering, and in the last relevant projects, well, the F-110 frigate and the S-80P built by Navantia for the Spanish Navy, where Genova participated in functional and detailed engineering. So this experience and this bet on Latin America, particularly for Colombia, is what I want to share with you. We are the world-class engineering office, which set up in Colombia, but for the world. Thank you. Thank you, Rear Admiral Carreño. We have a couple of questions to conclude. We would like to ask one of those. So from your point of view, which technological sector must be strengthened in the country to face the new challenges of building a new platform such as a warship? Well, it's a very important question, and I did not, during my presentation, I did not talk about that because that was not the intent of obviously, to tackle a project of this magnitude. The country must have leveraged, the Navy, the shipworks must have leveraged, as well as the industrial sector, on previous experiences. And I believe that Colombia has been doing it progressively through the construction initially of the river-going boats, but starting in the late 90s and early 2000s, the river-going fleet which the country received and which was autonomously developed by Colombia showed that there was a capacity to do so. Then using our own design, or purchase design, with that we were able to construct our own Coast Guard cutters, right? Offshore patrol vessels, the modernization of the surface fleet and the submarine fleet, obviously with cooperation and with international partners. But I believe that at the level of technologies where we must pay close attention are those that are associated to combat systems, the integration of a combat system, the interfaces of a combat system with such a complex platform as the frigate is. Point one. Point two, materials. The materials system is constantly evolving. This morning, Donato was telling us that Navantia, one of the development goals and stemming from the sustainable development goals, they mean to reduce their carbon footprint. So they need to build non-steel ships. So working with polymers, working with material transformation. So there's been a lot of investment, a lot of upgrading around this area of knowledge, energy. Perhaps today, all ships have internal combustion engines, and warships don't have the restrictions that commercial ships of over 500 tons would have, or in terms of the reduction of emissions, but they are adopted also by the state. Those commitments by the Sustainable Development Goals, that is reducing the carbon footprint. So how about ships that are run with electric engine, LNG, methanol, green hydrogen? Surely in a few years, we will see warships operating with these new sources of energy as they align with the SDGs. I'm sorry. And lastly, what? That says soft technology, but which is fundamental to the success and sustainability of the project. Therein kicks in the digital twin, not only as a support tool for decision making, but also to guarantee the sustainability of a project throughout the life cycle of it. I think that there are many other areas, but if I were to focus on some, that's where I would focus. Thank you, Rear Admiral, for your presentation. Thank you for participating in the event. Same to each and every one of the participants to this event. So, sí, al fin de la mañana voy a estar ocupado. Bueno,
De esta manera, agradecemos a las casi 1000 personas que estuvieron conectadas el día de hoy durante este primer día de COLOMBIAMAR 2021 y séptimo Congreso Internacional de Diseño e Ingeniería Naval CIDIN. Muchísimas gracias a todos por su asistencia y los esperamos mañana a partir de las 7:45 de la mañana a través de www.colombiamar.co. Muy buenas tardes.
No, esa no. Es la misma. Sí, pero a la hora. No, esta es la de la tarde. O después, perdón, después, no, o después. Where is this? is Cartagena.